Hey there! So today, we're going to tackle a really cool and fundamental skill in optics, drawing ray diagrams for a convex lens. Now, I know it sounds a little technical, but stick with me because by the end of this, you'll see how you can predict exactly how a lens creates an image, just by drawing a couple of simple, straight lines. It's pretty awesome.
So, to get us started, let's think about a little puzzle. Ever wonder how a movie projector takes this tiny little image on a piece of film or a digital chip and blows it up into that huge, sharp picture you see on the big screen? Well, it's not magic, it's pure physics. And the secret is all about understanding the path that light takes.
And the hero of this story, the amazing tool that makes all of this possible, is the convex lens. You might also hear it called a converging lens, and that name really tells you everything you need to know about its main job, to gather up light.
Okay, so what is a convex lens? Well, you can spot one because it's always thicker in the middle and gets thinner toward the edges. And that special curved shape is its superpower. It gives the lens this unique ability to grab parallel rays of light that pass through it and bend them inward, forcing them all to meet or converge at one single super focused point. You've probably seen a perfect example of this in action, right? If you take a magnifying glass out on a sunny day, you can focus that sunlight into a tiny, bright dot that can actually burn a piece of paper. What you're doing is gathering all those scattered sun rays and concentrating their energy into one spot. And that very ability to focus light is the absolute key to how a lens forms an image.
So, how can we possibly predict where an image is going to form? Well, the great news is you don't need any complicated math or fancy computers. It turns out light follows a few very simple, very reliable rules when it passes through a convex lens. Think of them as the rules of the road for light. Once you know them, you're all set. All right, here are the three main rules. But pro tip, you only need to draw two of these rays to find out exactly where your image is. For our diagram, we're going to use the first two, because they're the easiest. So, rule 1, the parallel ray. Any ray of light that comes in parallel to the main center line, we call that the principal axis, will hit the lens and get bent so it passes right through the focal point on the other side. Simple. Rule 2 is even easier, the center ray. Any ray that goes straight through the dead center of the lens just keeps going in a perfectly straight line. It doesn't bend at all. That's it. With just those two rules, we can find any image. Okay, enough with the theory. It's time to actually put these rules to work. Let's get our pencils out, so to speak, and draw a diagram for a really specific and really important setup.
So here's our scenario. We're going to place our object, we'll use a simple arrow, in a very particular spot. It's going to be somewhere between the focal point, let's call it F, and a point that's twice as far, or 2F. Now, this isn't just a random spot. This specific placement is the secret sauce behind how projectors actually work.
Let's go. Time to apply rule number 1. We're going to draw our first light ray, starting from the very top of our arrow, and we're going to draw it parallel to that center line until it hits the lens. As soon as it hits the lens, what does it do? It bends and passes right through that focal point on the far side. See? Perfect. Okay, one ray down. Now for our second ray, using that super simple rule number 2. We draw another line from the top of our object, but this time it goes straight through the very center of the lens. And remember, this ray is the rebel. It doesn't bend at all. It just keeps on going in a straight line. And look at that. It crosses our first ray right at this point here. And that is the aha moment. That exact spot where our two rays intersect, that tells us precisely where the top of our new image is going to be. So all we have to do is draw a new arrow from the center axis down to that intersection point, and boom, we've just found our image.
So we did it. We drew the diagram, but what did we actually create? What does this new image look like? Let's break it down and analyze its 3 key characteristics. First off, and this is so important, because those light rays are physically meeting and crossing at that point, they create what physicists call a real image. And real means you can project it. If you were to put a screen or a piece of paper right at that spot, a sharp, focused image would appear on it, just like the screen in a movie theater.
Second, just look at how it's oriented. Our original arrow was pointing up, right? But the image we created is pointing down. It's completely flipped over or inverted. This is exactly why, if you've ever used an old slide projector, you have to put the slides in upside down. The lens is going to flip them anyway, so you plan ahead.
And finally, the third characteristic. Just compare the sizes. Our new image arrow is obviously way taller than the original object arrow we started with. Our image has been magnified, or made larger, And that, of course, is the whole projection part of a projector, taking something small and making it big enough for a whole room of people to see.
So let's do a quick recap. When we place an object between f and 2f, the convex lens creates an image that is 1. Real, which means we can project it onto a screen. 2. Inverted, which is why things go in upside down. And 3. Magnified, which is the whole point. Those 3 things right there are the basic recipe for a projector.
And this principle of creating a real magnified image, it's not just for projectors. This exact same process happens inside a microscope. The very first lens, the one closest to the slide, does precisely what we just drew. It creates a magnified, real, and inverted image of that tiny little specimen. Then a second lens magnifies that image again for you to see. So what we've drawn today is literally the first critical step to seeing the entire microscopic world.
So there you have it. We've basically just built the optical heart of a projector from scratch. But here's a question for you. What do you think would happen if you took that object and moved it even closer to the lens, so it's inside the focal point? The rules for drawing the rays stay the same, but the result is completely different. And that's the secret behind how a simple magnifying glass works, and it's a fantastic question to dig into next.